11. Okay, and that's it. Let me just go back to the definition. This is something that I leave to you to explore. Basically, it's a subdivision of the water footprint between internal and external water footprint. So internal means that it's directly taken by countries, water, and external means that it's important. It's not really something that you need to memorize. And now let's go into, and here I am moving into the third lecture in my website and in IOL. So the lecture on sustainability in the 21st century is over, and then I'm moving into the details of water resources. So here you see a picture that basically tells you again what I anticipated in terms of percentage of salt water. This is total global water. Keep in mind that water is not generated and is not destroyed. Unless something really bad happens, like it happened on Mars, which I think I already mentioned to you. Water, the amount of water, the total volume of water on Earth is a constant. And if you look at the total global water, as I said, fresh water is about 3%. Here you see 2.5 because there is a 0. Something contribution by other kind of saline water besides the oceans, like internal salt lakes. You know that there is, for instance, the Dead Sea, it's an internal lake that is saltier than the sea. But there are other internal lakes with a high salinity and with a salinity that impedes, doesn't allow the use of water for civil use or for agriculture. And therefore, the total amount of fresh water available is, according to this estimate, is about 2.5%, and some other sources say 3%, so the order of magnitude is 3%. Now, if you explode this 2.5% in this second column, this is fresh water, you see that there is a 70% that you cannot use. I already anticipated that. It is only one drop over 100 that you can use, and this drop is composed, this 30% of 3%, so this 1% total, is made up by groundwater, 30%, and surface water, 1.2%. There is one important thing to notice here. If you look at these pictures, it seems like surface water is not important for delivering water resources for water uses. But this is a static picture. This only depicts storage. So it looks like you take a picture of Earth, and there is water in the rivers, and you compute the volume at a given time. But water in the rivers has an important feature. It moves. It is renewing very fast, which means that if you take water from a river, after 1 second, you have other water available. So at a certain time, surface water is only a small volume of total water. But given that it's renewing very quickly, it's an important source. Groundwater is not renewing so quickly. So it is true that if you look at the instantaneous picture, groundwater is 30 times surface water in terms of volume. That's true. But given that groundwater is not renewing quickly, actually, it happens that water withdrawals, water supply, is delivered to people, to industries, and to agricultures in proportion that are not 30 to 1. It depends on the country, it depends on the context, but this proportion in some cases is half-half. because, as I said, surface water is renewing very quickly. So you don't have to underestimate the importance of surface water. If you look at surface water and you explode it in the third column, you see that there is still a part that cannot be used because it's not. Basically it's in solid state. It's not part of permanent glacier and ice caps, but it's a part of ice. It's ice that is not permanent, but still it cannot be used, at least in some seasons. And then you have the lakes, about 20%. If you look at rivers, is 0.5% of this 1% of this 1%. So it means that rivers in principle have a very small volume. But again, water in rivers is extremely important. So basically our main water sources are surface water, rivers, only a few sources are from lakes, and then there is groundwater. But groundwater we have to be very careful because it requires energy and it may take a lot of time to be renewed, maybe not renewable in short time steps. This is a picture of the spatial distribution of rainfall and at the global level in different months. Where you see white, it means no rain, green is moderate, like Italy is moderate, and dark blue is very rainy. So basically dark blue is 6 millimeters per day. What does this mean? This is extremely important because I'm talking again of orders of magnitude. 6 millimeters per day means about 2 meters of water per year, a little bit more than that. Now, what does this mean Italy? So Italy is green. So green is 2 millimeters per day, which means like 800, 750 millimeters per year. So there is a basic question that I wanted to ask you before starting this course, like what do you think is the annual amount of rainfall in Bologna or in the place where you live? And I tell you, only a few students provide a reasonable reply. So the correct reply for Bologna is about 1 meter per year of rain. And why I am interested in rain? Because, of course, the driver of water resources is precipitation. When I say rain, okay, precipitation includes also snow, and I should say that the driver is precipitation. Here you see that it's rainfall, but actually it includes, it's precipitation actually, it includes snow. So, as I said, the order of magnitude is for Italy, the rainier region of Italy is Friuli Venezia Giulia. It's in the northeast, where in some places we have about 2.5 meters per year in the mountains. Usually you get more rain in the mountains than in the lower lands, and for obvious reasons. And then the minimum is in Sicily, where we have about 600 millimeters per year of rain. So this is the range in Italy, and it is an order of magnitude that you have to keep into account. Because, you know, it's something that at a job interview people may check if you know. So the knowledge of the orders of magnitude, again, for an engineer is essential. And given that I'm teaching water resources management, water supply, etc., the orders, important orders of magnitude are the annual amount of rain. Another important order of magnitude is extreme rain. To get an idea of what could be an extreme rain, like in 1 hour, and an hour of a very heavy rain, how much water can fall down here in Bologna. This is another important order of magnitude, we may speak about it. Another important order of magnitude is river flow. So to get an idea of what is the average flow of the Po River. I say the Po River because we are in Italy and it's the most important river of Italy. But if you come from another country, you have a most important river in your country, or several most important rivers. It's important that you know the average flow. Average means, in the long term, you compute an average. So for the Po River, this average is about 1,500 cubic meters per second. 1500 cubic meters per second.
One thing, so you said like more or less is like 6 millimeters per day is 2 liters per year?
It's 2 meters per year.
2 meters per
Yeah, rainfall is measured usually in depth.
Yeah, exactly. Okay, okay. So, okay, 2 meters.
Yeah, and you're touching an important issue, which is the equivalence between liters. Liter is a unit of volume, and I already mentioned it. Usually volume of water is measured in cubic meters, but for small amounts in liters. And you have to know that 1 cubic meter is 1,000 liters. This is something that you have to have very clear. And sometimes I ask this question at the exam, and not everybody provides a correct reply. Not everybody. So like, okay, 1 cubic meter, how many liters? And some people say 100, some people say 10,000. Or some people say, I really don't know. So, you may think that it's trivial, but I tell you, the trivial questions are the more tricky, because if you don't know the reply, it's embarrassing. Okay, and let's see. This is a climate classification, and it is proposed on the slides, and basically it's a climate classification that tells you what is the amount of precipitation in it's mainly based on the amount of precipitation. It's the most used climate classification at the international level. Keep in mind that when you talk about water resources, water resource system and sustainability, you need to know something about climate. And maybe the basic behavior of climate, like the rainier region of the world, the hottest region of the world, and does it rain more at the equator or in the very north part of Europe? This is something that you have to keep into account. So it's sufficient if you look at a map like this, and you see that equator is more or less here, and at the equator you have a lot of rain. It's something that you have to know. So it's not something that I ask at the exam, but this is the reason why I'm putting it here is that really it's important for you, knowledge of climate. This is the distribution of water resources, and distribution of water resources basically reflects the distribution of rain, not everywhere, but still. Sorry, 1 second, I'm trying to remove this. Okay. And not really everywhere, but here the dark blue is a lot of water, and the light blue is less water, the green is water scarcity, etc. And again, this is a picture that allows you to get an overall overview. Look here, this acronym, FAO is an international organization. I have an amnesty now, I don't remember. It's Federal Agricultural Organization, something like that. And it's international everywhere, so it's not federal. It's a Food and Agriculture Organization. It's an international organization that has the mission to focus on water and water resources assessment. They have a database, Aquastat, which is free. This database is extremely interesting. So, because for each country quantifies the amount of renewable fresh water, the total amount of fresh water, the water demands. It's extremely nice, extremely interesting to get an overview of water demands, water use, water availability, freshwater availability. And they provide the result through maps. This is a map that I built through the database. So you can provide the results in the form of a graph. And it's extremely interesting. I suggest you that you look, for instance, in your country, if you are from Italy as well, to look what is the amount of renewable fresh water, the amount of fresh water, the water demands, And if you want to make a presentation during in the context of these interacting activities, like this is my country, and this is from Aquastat, the amount of fresh water, etc. And a presentation is 5 minutes, so it would be nice. It would be really nice. And you can focus just on your country or to some countries. If you see that the numbers are too few, to fill 5 minutes, you can focus on another country for comparison, like Italy and your country, or United States and your country. This would be interesting. And it's very easy. You just have to Google Aquastat, you get in, and you will see that it's easy to get the data. And it's useful for your profession, for your future profession. It's updated, and so here it's 2015, but it's updated up to today. Okay, and this is another graph from Aquastat. This is global distribution of the proportion of renewable water resources that is withdrawn. So basically, what does this picture tell you? Basically, if the proportion of renewable water resources that is withdrawn is low, this is a problem, because it means that what is withdrawn is non-renewable. And therefore, if you look at the countries with the darker colors, it means that they are not exploiting too many non-renewable resources. Still, they may use a limited amount of water. They may experience water scarcity. So this graph is not telling you what are the countries that don't suffer from lack of water, because you see that here Africa, the desert of Sahara, it seems not suffering. No. This highlights the countries that are running the risk of exhausting their water sources. So the light, like South of America, it's the countries where the use of non-renewables is more concerning. And this is the global distribution of water withdrawn per inhabitant. And this is dark is 1,000 cubic meters per year. So you see here the countries that use more water. The colors actually in the website are more exciting, meaning that here it's difficult to make a difference, to notice the differences. Indeed, it's the color scale that is not correct here. And this is another graph, global distribution of proportion of total water withdrawal that is withdrawn for agriculture. These are useful maps. In order, useful maps, again, to gain some sensitivity, to gain some global knowledge. No question at the exam on this. I'm not asking what is the country that uses more water for agriculture. Absolutely not. And also it's an example of the power of Aquastat. This picture is just to show you seasonality. So, up to now, we spoke about spatial distribution. Why spatial distribution is important? Because I told you that we have enough water available, but it's not evenly distributed. So, and it's not evenly distributed in space, but also in time. So far I wanted to give you an overview of the heterogeneous distribution of water in space. Now let's briefly mention time. Even if you have a lot of water in that country, it may be available at the time that is not at the right time. So here you can see seasonality. Seasonality, which is different in several, these are pictures related to average monthly flow for selected European rivers. Here there are the names, I'm not reading the names. You can see the drop that connects this graph to the related country. And you see that seasonality is different in the same country, it depends on climate essentially, but seasonality is extremely important because you may have rivers that are experience low flows during summer. You may have rivers that experience high flow during summer. So it's important that water sources are complementary. And you have the problem in any case of the time distribution that it's not uniform. and which means that you need to store water at the local level. So the dams have the purpose of stabilizing water resources availability against seasonality. You store water when water exceeds your demand, and you release water when demand is exceeding water resources availability. Now let's look at possible solution. Let's start to look at possible solution. So now, after the assessment of distribution of water resources, total amount of water resources, now let's suppose that we need water resources management. We need to manage water efficiently, which means that we are experiencing water scarcity, basically. So what are the solutions? Okay, we already mentioned that we have structural solutions, green solutions, we may have. So one first solution, which was traditionally applied, is increasing water availability, water supply. And increasing water supply means that you need to mobilize more water. Mobilize more water means that if you are taking water from rivers, you need to increase the amount of water that is withdrawn. If you take water from the groundwater, you have to be a bit careful because you need to get more water from there, and you have to make sure that it's renewable. From rivers, getting more water may imply the construction of dams, and therefore this is...
La disturbo se assisto agli ultimi 5 minuti.
No, assolutamente, ma proprio saranno 2 minuti, venga pure. So, the amount of water, sorry, it's a colleague and he's joking. The amount of water, increasing the amount of water that is available means, like, as I said, building more dams, etc. You know, this solution is the one that was classically applied, but it has environmental issues, of course, because if you mobilize more water, it means that you are taking water from somewhere and you are deprivating some water bodies of their water content. So this is something that is widely applied, but at the same time criticized. On the other hand, this is a solution that is very convincing. If you talk with the people, with stakeholders that experience water scarcity, and you tell them, I give you more water, they are happy, basically. And instead, if you propose other solutions that may be equally effective, but are not so convincing, it may be difficult to, you know, at the end of the story, to put them into practice. This is an example of cost of water supply, because if you want to increase the water supply, of course, you have to consider, you remember the economic pillar, you have to consider the costs. And basically this tells you that groundwater has different costs depending on the depth of the water table. Surface water usually has a cost that is not very relevant. Groundwater usually has a higher cost. In California, in southern California, groundwater is readily available and therefore it's not very costly. But in general, for instance in Italy, groundwater is more expensive with respect to surface water. And if you look at desalination, you see by far the highest cost. And this is the reason that I mentioned to you before why desalination is still not an option at large scale. Besides the costs, it's not an option because it takes a lot of time. So it's still not feasible. A second solution is water demand control and regulation to water scarcity. And this is the type of solution that I mentioned to you. Sometimes it's not really liked by the public and stakeholders because it's not convincing. On the other hand, there is to say that it's not convincing, but it's a real solution, because if you think about water losses, and this is mentioned here, water losses in water supply systems vary between 50% of what is withdrawn in open channel flow. 50%, it means that half of the water is lost for evaporation or infiltration in the ground or losses anyway. Even if we consider pressure, under pressure flow, pressured flow, the losses are around 30% if the system is very efficient, and they can reach like 40–45% if the system is not efficient, because it's difficult to control leakages and water losses in general. These are important numbers. It means that if we were able, probably it's impossible, but if we were able to reduce significantly these water losses, it means that your storage, your number of dams could be reduced by 1/2, or let's say 30%. And it's extremely convincing. But on the other hand, you know, when you talk about reducing losses, people are not really happy, because you don't talk about something that can be seen. Instead, if you build a dam, it's something that can be seen. And this is the reason why it's more convincing. I think we can stop here, and then we get it back. So on Monday, we meet at 9:15. I promise I'll be timely, and with the computer already set up. And so let's start at 9:15 sharp, and at 10, from 10 to 11, we will have the seminar. Okay? Good, thank you.